We are now going to study one of the most important safety considerations in long-haul flying. It is known as point of equal time. This is often abbreviated to PET. It is also called equal time point, which can be abbreviated to ETP. An older name for it is critical point. If you see any of these terms or abbreviations, they all mean the same thing. The majority of transport flights take place over routes where there are many en route alternate aerodromes. In the event of an emergency requiring an in-flight diversion, there are usually several available. However, over some routes, there may be no diversion available over a large part of the flight. Oceanic transits, such as this one over the Atlantic, are one example. After passing Gander, which is the most easterly point of Canada, the next available airfield is Shannon in Ireland. This is a distance of over 1,700 nautical miles. Should a failure occur at some point over the Atlantic Ocean, the most important consideration is to get the aircraft on the ground as soon as possible. This is a point of equal time problem. The point of equal time is defined as that point along track from which it will take the same time to fly to one of two airfields. Therefore, if an emergency takes place after the PET, it is quicker to go on. And if before the PET, it is quicker to return. The point of equal time therefore occurs when time on equals time home. The determination of the PET is a time problem, and there will always be sufficient planned fuel for the aircraft to fly to one of the nominated airfields. The amount of fuel carried is not a consideration. Point of equal time may be calculated between the departure and destination airfields, as in this example, or it may be calculated for that part of the route for which no diversion airfield exists. Let's look at a practical example and see what factors determine point of equal time. Let's assume a route 400 nautical miles long with no diversion between the start and finish airfields. Let's assume that the aircraft has a constant TAS of 200 knots and that there is no wind. In that case, the calculation is a simple one. The point of equal time is also the point of equal distance. It occurs halfway along the route. We do not take the time to turn into consideration. Turning through 180 degrees at rate 1, 3 degrees a second, takes only 1 minute. This is negligible compared with the total flight time. If we continue onwards, we will have 200 nautical miles to cover at a ground speed of 200 knots. But also, if we come home, we will also have 200 nautical miles to cover at a ground speed of 200 knots. Now, we'll leave the halfway mark on the diagram, just for reference. But we'll look at the effect of a 50-knot headwind all the way along the route. Now the ground speed onwards will be 150 knots, while the ground speed home is 250. The point of equal time has now moved forwards to a distance of 250 miles from the departure point. The distance onwards will be 150 miles at 150 knots, and the distance home will be 250 miles at 250 knots. The effect of the headwind has therefore been to move the point of equal time towards the direction that the wind is coming from. What if it had been a tailwind? Let's now imagine that we're flying over the same route on a different day, and this time the mean wind over the whole route is a tail component of 30 knots. In this case, the ground speed onwards will be 230 knots, whilst the ground speed home is 170. The point of equal time moves backwards to a distance of 170 miles from the departure point. The distance onwards will be 230 miles at 230 knots, and the distance home will be 170 miles at 170 knots. The effect of the tailwind has also been to move the point of equal time towards the direction that the wind is coming from. So the effect of any wind component along track, whether head or tail, is always to move the point of equal time towards the direction that the wind is coming from. Let's now derive the formula to calculate point of equal time in general terms using algebra. We'll call the distance between our two diversion airfields d. Somewhere along the route is the point of equal time. We don't know where it is yet. This is what the equation is going to find out for us. So it's an unknown distance, x. We'll call the onward ground speed from the point of equal time O, and the homebound ground speed h. The basic definition of point of equal time means that the time onwards must be the same as the time home. But time is distance divided by ground speed. For example, if you have 100 miles to drive and your speed is 50 miles an hour, it would take you 2 hours. The distance home is x, and the ground speed home is h. If the total distance is d, and the distance home from the PET is x, then the remaining distance onwards from the PET must be d minus x. And the ground speed onwards is O. We are trying to find x, so we need to isolate it on one side of the equation. We start by cross-multiplying. This gives us xo equals h, open brackets, d minus x, close brackets. Multiplying out, we get xo equals dh minus xh. We now need to get the term xh onto the left-hand side of the equation. So we bring it across, changing the sign as we do so. This gives us xo plus xh equals dh. Factorise the left-hand side to isolate x. And now divide both sides by O plus h. This gives the final equation x equals dh over O plus h. This is the one that you must remember. You will not be examined on the derivation which we have just shown. We put it in to demonstrate that the equation is based on good logical algebra and is correct. But whether you remember that part or not, you must be able to recall the result, which is that x equals dh over O plus h. This is the starting point for all point of equal time questions. We'll now try some simple worked examples using the formula, and demonstrate that the algebra gives the same results as our earlier basic navigation calculations. Assume a total distance of 500 nautical miles and a true airspeed of 300 knots. Let's start off with a still air case. In this situation, O, the onward ground speed, is 300 knots. And h, the homebound ground speed, is also 300 knots. Let's write the formula down. X equals dh over O plus h. D is 500, and O and h are both 300. So x, the distance to the point of equal time, is 500 times 300 over 600, which comes to 250 nautical miles. This is halfway, which was exactly what we found when we did a still air example earlier. Now let's see what the effect of 60 knots headwind will be. Again, the total distance is 500 nautical miles, and the true airspeed is 300 knots. However, this time we have 60 knots headwind. Now O, the onward ground speed, will be the combination of the 300 knots TAS and the 60 knots headwind. This gives an onwards ground speed of 240 knots. However, if we return, the headwind becomes a tailwind, and H, the homebound ground speed, becomes 360 knots. Here's the formula. X equals dH over O plus H. D is 500, and O is 240, and H is 360. This means that x, the distance to the point of equal time, is now 500 times 360 over 600, which comes to 300 nautical miles. So using the algebra confirms what we have shown with simple navigation calculations earlier. The effect of a wind component along track is to move the point of equal time towards the direction that the wind is coming from. Now let's consider 60 knots tailwind. This time O, the outbound ground speed, will be the combination of the 300 knots TAS and the 60 knots tailwind. This gives an onwards ground speed of 360 knots. However, if we return, the tailwind becomes a headwind, and H, the homebound ground speed, becomes 240 knots. Here's the formula again. X equals dH over O plus H. D is 500, and O is 360, and H is 240. This means that X now becomes 500 times 240 over 600, which comes to 200 nautical miles. And again, using the algebra confirms what we had shown with simple navigation calculations earlier. The effect of a wind component along track is to move the point of equal time towards the direction that the wind is coming from. So let's summarize this lesson. The point of equal time is defined as that point along track from which it will take the same time to fly to one of two airfields. It is calculated from a simple formula, which must be learnt. D is the distance between the two airfields being considered. X is the distance from the start to the point of equal time. The onward ground speed from the point of equal time is called O, and the homebound ground speed is called H. The effect of any wind component along track is always to move the point of equal time towards the direction that the wind is coming from. This is true whether it is a headwind or a tailwind.